So far, we looked into the if-else statement where we evaluate a condition, and if the condition is true, we execute statement 1. If the condition is false, we execute statement 2. But sometimes we want to take an action by evaluating 2 or more conditions. Let's look at some examples. Let's say we would like to execute statement 1 if condition 1 and condition 2 are true. So we have two different conditions now, condition 1 and condition 2, and we execute statement 1 only if both of them are true. The second example says evaluate the statement 1, only if condition 1 or condition 2 is true. That means we are going to execute the statement when either condition 1 is true or condition 2 is true. So either of the conditions, if either one of these conditions is true, we will be executing statement 1. If both of them are false, then we would not be executing statement 1. And lastly, we could say if not condition 1, then statement 1, which means if the condition is false, then not of that condition. So you basically negate the result of that condition. So if the condition is false, when you negate it, it becomes true. So we execute statement 1. But if the condition is true, then when you negate it, it becomes false. So then you don't execute statement 1. These are called logical operators in C++, and that they let us to form complex relational expressions. So just to summarize, we have got and, or, and not. If you look at the symbols representing these logical operators, we see the logical AND operator is designated by ampersand, ampersand. The logical OR operator is designated by two bar symbols, and the logical NOT operator is designated by the exclamation point symbol. Since C++11, you can actually use AND, OR, and NOT as keywords to mean the same thing. Before C++11, these did not exist. You're only able to use ampersand, ampersand to mean logical AND, bar, bar to mean logical OR, and NOT to mean logical NOT. But since C++11, you can actually use these keywords to mean the same thing. And for those of you who are Python programmers, you would know that Python actually uses these keywords and, or, and not to mean these logical operators. So basically C++ added what was already part of Python into the language. So let's look at the truth tables for and, or, and not. So let's say we have two logical conditions that we are evaluating. This is condition 1, this is condition 2, and this is AND, logical AND. You can see that logical AND is true only if both conditions are true. So if both condition 1 and condition 2 is true, then the result of condition 1 and condition 2 is true. Otherwise, we always the expression evaluates to false. I mean, that's the general idea, right? So you're basically saying execute this statement if condition 1 and condition 2 is true. So both of the conditions have to be true in order for the complex expression, the compound expression to be true. And in the case of OR, logical OR, the reverse is true, meaning the condition, the compound expression is false only if both condition 1 and condition 2 is false. So you can see it in here. So condition 1 is false, condition 2 is false, then the overall expression would be false. But if any of these expressions is true, like if condition 1 is true, then result have to be true, or if condition 2 is true, then the result has to be true. And not is basically taking whatever the value of the condition and negating it. So if the value of the condition is false, then by negating it, you get true. And if the value of the expression is true, and you negate it, you get false. Let's look at some examples. Assume that we've got two integer variables, x is equal to 3, y is equal to 4. Let's look at this expression where you are first evaluating x greater than or equal to 3. So x is 3. Is 3 greater than or equal to 3? Yes. So this part of the equation, condition 1, is true. Let's look at condition 2. It basically says y is equal to 4. the value of y is 4. So 4 is 4 equal to 4? Yes. So condition 1 is true. Condition 2 is true. When you say condition 1 and condition 2, if both of them are true, the expression has to evaluate to true. The second expression says x less than 0 or y is greater than 0. So let's look at x. The value of x is 3. Is 3 less than 0? No. So this condition 1 is false. But if the condition 2 is true, then the overall expression would evaluate to true. Let's look at the second part of the expression. The second condition is y greater than 0? Yes, because the value of y is 4. 4 is greater than 0. So the first condition is false, but the second condition evaluates to true. That means condition 1 or condition 2 evaluates to true, because the second condition being true makes the overall expression true. The third one, x is equal to 3 and y is equal to 5. X is 3, as we can see, the value of x is 3. So the first part of the expression evaluates to true, but the second part does not evaluate to true because the value of y is 4, but we are checking y is equal to 5. So x is equal to true, yes. X is equal to 3 is true, but y is equal to 5 is false. So we've got true and false. That means the overall result will be false. And the last one is negating the value of this expression. So let's look at it. X is equal to 0. Is that true? No. X is 3, so 3 is equal to 0 is false. And y is equal to 0, so y is 4, so 4 is equal to 0, that's also false. So this is false, and when you AND them, you get a false result. And when you negate the false result, so false negated is true. So this should be true. It's not true, of course. This should have been true. So the expression inside the parentheses evaluates to false, but when we negate it, the result becomes. Let's look into A and B a little bit deeper. So think about it. If the first operand, the first condition A, evaluates to false, then regardless of what the value of B is, the overall equation A and B evaluates to false, because this is false, and whatever the value of B is, false, and the B would always be false. For A or B, if the first operand evaluates to true, so if the value of the condition A is true, then regardless of the value of the second operand, A or B evaluates to true, because true or whatever is always true. Because of this, some programming languages, including C++, do not evaluate the second operand when the result is known by the first operand alone. This is called short circuit or lazy evaluation. So to recap, in the case of A and B, as soon as the value of the first condition A is false, B is not evaluated. And in the case of A or B, when the compiler evaluates the first condition A and determines that the value of A is true, it does not evaluate B. That's not necessary, because then A or B is already true. So again, this is called short circuit or lazy evaluation. Let's look at a common error that you might encounter as a programmer. Consider the following code. What do you think will get printed on the screen? So we've got integer A is equal to 2, integer B is equal to 5, and apparently the programmer is trying to say if A and B, then we are in the inside the if part, else we are inside the else part. So apparently, by just looking at the program from the face value, you would think that program is trying to say A logical and B. And if you think about it, A is 2, so in C++, any non-zero value is considered to be true. That means A is true, B is true because B is 5. So you would think that A and B would be true, and we'll see inside the if part on the screen. But when we execute this code, we'll see inside the else part. So the else part getting executed, and you will get confused. I mean, again, what's going on? And the reason is, when you look at the program a little bit carefully, you would see that instead of typing a and b ampersand b, which is the logical or operator, a logical AND operator, the programmer typed a and b single ampersand, which is the bitwise AND operator. So bitwise AND is very similar in appearance to the logical AND, but it works differently. So remember that bitwise operators work on a bit level, meaning that it's going to take the AND logical AND on a bit by bit basis, which means it's going to take the first bit, so 1 and 0, that's 0, 1 and 0 is 0, and then 1 and 0 is 0. So by doing a bitwise AND operator, your 2 bitwise AND 5 is actually 0, which is false in C++. That's why the compiler says, okay, A bitwise and B, that evaluates to false. So we are going to jump to the else part. Again, the intention of the programmer is a logical AND B. I mean, that's probably what the user was trying to, the programmer was trying to type it in here. But by mistake, instead of typing 2 ampersand symbols, the programmer typed 1 ampersand symbol, and that leads to this unexpected behavior. And this is a very common error and is usually very difficult to find. Again, this problem is very similar to typing single equality symbol to mean the equality operator. Remember, single equality symbol in C++ is the assignment operator. In order to write the equality operator, you have to type in equal. So 2 equal symbols designate the relational equality operator. The same applies here. So in order to say a logical AND B, you have to say a and B. And also, this also applies to logical OR. So in order to say logical OR, you have to say a bar B instead of a single bar, because a single bar is again a bitwise OR operator, and you would get unexpected results if you do that. So again, be very careful when you're using the logical AND operator, and make sure that you type in and to mean the logical AND operator. We have pretty much covered all the operators in C++, and here is an extended table that's showing the precedence and associated with the rules for almost all operators in C++. So at the top, you see the operators with the highest precedence, the parentheses, the square bracket, and there are 2 more operators that you would see when you look into objects, structures, and pointers. And at the bottom, you see the comma operator, which has the lowest priority. So from the top, highest priority, towards the bottom, you see the increment and decrement operators, right? Unary increment and unary decrement, unary plus and unary minus, then multiplication, division, and modulo. So among the arithmetic operators, multiplication, division, and modulo have the highest priority. Then you see plus and minus, so addition and subtraction, which have the next highest precedence, but they have lower precedence than multiplication, division, and modulo operators. Then comes the relational operators: equality, not equal, less than or equal to, greater than equal to, and greater. Then the logical operators. So the logical operators are not, and, or. So again, not has the higher precedence among the logical operators, then and, then or. And at the bottom, we see the assignment operator, either regular assignment or compound assignment operators. And at the bottom, you see the comma operator. So that's pretty much it as far as precedence and associated with the rules are concerned. Let's now look at an example where we are making use of the logical operators. Assume that you have a rectangle defined by 2 x coordinates, x1 and x2, and 2 y coordinates, y1 and y2. So the rectangle is defined from x1 to x2, right, on the x direction, and from y1 to y2 on the y direction. And you have a point xy, and you would like to determine whether xy, this point, is inside the rectangle. I'm going to assume that the boundaries are considered to be inside the rectangle. All right, so here's how we can test it. A point xy is inside the rectangle if the x coordinate is in between x1 and x2, equal in, even if it's equal to x1 or x2, and y coordinate is in between y1 and y2. And this is how you can write it. So you can say we are now testing for containment of the point inside the rectangle. So a point is inside the rectangle if x is greater than or equal to x1. So if x is greater than or equal to x1, and x is less than or equal to x2. So if x is in between x1 and x2, then the x coordinate is in between. But now we still have to test whether the y coordinate is in between y1 and y2. So then we say y is greater than or equal to y1, so it is above y1, and y is less than or equal to y2, so it should be less than or equal to y2. As you can see, we have 4 conditions for a point to be inside the rectangle. So x coordinate has to be in between x1 and x2, and the y coordinate has to be in between y1 and y2. If all 4 conditions are satisfied, then the point is inside the rectangle. Otherwise, the point is outside of the rectangle. This is example 12. So let me go to that example. This is example 12. Assume that the rectangle is defined from x1 5 to 10, and from in the y coordinate it's from 3 to 12, and my point is 5 and 7. So if you think about it, x is 6, which is in between 5 and 10. Y is 7, which is in between 3 and 12. So we should see the point is inside the rectangle. But let me just show you that that's the case. Let me go into the debug mode, and we're going to now come here. All right, so we are now here. As you can see, these are the values of x1, x2, y1, y2, and x and y. Because the point is inside the rectangle, we are going to go into the if part of our equation and say point is inside the rectangle. Correct? All right, so let's move on. We can actually test for not containment. In the previous example, we test for containment, saying that if x is in between x1 and x2 and y is in between y1 and y2, the point is inside the rectangle. But what we can do is we can take that condition and negate it, right? If we apply now the negation operator, the not operator, what we are basically saying is this condition is testing whether the point is inside the rectangle. If I negate it, then I'm now testing for not containment. So if not of this condition is true, then the point is outside the rectangle, right? Remember, the condition, if this condition is true, the point is inside the rectangle. If I take the negation, if I negate it, then I'm basically saying I'm now testing for not containment if the point is outside of the rectangle. And here is that code. So basically I am taking, remember, this condition is testing whether the point is inside the rectangle. By negating it, I'm testing for not containment. So basically the condition will be true, and negating it will make it false. So we'll go to the else part, saying that the point is inside the rectangle. All right. Another way to write this same condition is by applying what's called the De Morgan's law, where we distribute this negation operator inside the parentheses, and by that's going to change the operators. So that's gonna negate the operators in a sense, and this is what you're going to get. So now you're going to get if x, we are still testing for not containment, but now the test is if x is less than x1, or if x is greater than x2, or if y is less than y1, or if y is greater than y2, then the point is outside the rectangle. Again, this test is for not containment. Otherwise, the point is inside. And if you think about it, you can visualize it. So assume that, consider the point x. If the value of the point x is less than x1, so it must be somewhere here, right? So think about it. So if the point is somewhere here, meaning that the x coordinate of the point is less than x1, it's definitely not inside the rectangle. Or if the point is somewhere here where the x-coordinate of the point is greater than x2, which is the second condition. So if x is greater than x2, then it's definitely not inside the rectangle. The third condition says if the y-coordinate is less than y1, let's put it in here. So if, as you can see, the y-coordinate of the point is less than y1, that means it's definitely not inside the rectangle. And the fourth condition tests whether the y-coordinate of the point is greater than y2. So, and that's the last condition. So this is again testing for not inside, not containment of the point inside the rectangle. If that's the case, the point is definitely outside of the rectangle. Otherwise, it's inside. So this is our third condition. Again, using the same information, same x and y coordinates for rectangle and the point, we will again say, we're going to jump to the else part and say the point is inside the rectangle. And that's it. So now we have pretty much seen three ways to implement the containment. One is testing for containment. The second one is testing for not containment. And the third condition is basically making this operation expression simpler by distributing this negation operator inside the expression that's inside. You're going to see that this is called the De Morgan's law when you take discrete computation structures or logic classes later on. And this applying the De Morgan's law, it's going to change this expression into this, which is basically going to change the operators and also the logical operators. So n becomes or, greater than or equal to becomes less than, and so on and so forth. So basically, three ways to achieve the same thing. Let me test another point which is outside. So let me put an x that's less than x1. So let me put a 3, for example. Obviously, 3 is less than 5. So this point is definitely outside of the rectangle. And when we run it, all three if statements should tell me that the point is outside of the rectangle, as you can see in here. As I mentioned, since C++ 11, the keywords and, or, and not have been added to the language, the C++, to mean logical and, logical or, and logical not. So here is an example where we've got two Boolean variables, condition 1 and condition 2. Assume that condition 1 is true, condition 2 is false, and we are saying condition 1 and condition 2. Again, instead of using ampersand to mean logical and, I'm using the new keyword and. So condition 1 and condition 2. Of course, this is false because for this condition, the compound statement to be true, in a sense, both of them have to be true. So condition 1 is true, the condition is false. That means this is going to be false. Else if condition 1 or condition 2, again, I'm using the new keyword or, because one of them is true, this is going to evaluate to true. Here I'm doing if not condition 1, and here I'm doing if not condition 2. So this is example 13. Actually, let me go ahead and execute this in the debug mode so that you can see what gets printed on the screen. So we are here, condition 1 is true, condition 2 is false. Condition 1 and condition 2 will be false because one of the conditions is false. We are now going to go to else if, where we are going to say if condition 1 or condition 2, and because one of the conditions is true, this evaluates to true, and we'll execute at least one condition is true. And we are now executing if not condition 1. As you can see, condition 1 is true, so if not condition 1 would be false. That's why we are not going to execute the if statement inside the if. And lastly, if not condition 2. So condition 2 is false. Not of condition 2 would be true. So we'll be going in and saying condition 2 is false. All right, so that's another way to use these logical operators using the new keywords. Again, it's up to you which one you use. So you could use either ampersand to mean logical and bar to mean logical or, and exclamation mark to mean logical not. Let me just execute this so that it's going to also compile and run. It's all up to you which one you use. So before C++11, these were the only logical operators symbols that you could use. But now with C++11, since C++11, you are actually able to use these new keywords to mean logical and logical or and logical not. So it doesn't really matter which one you use, just stick to a convention. Of course, if you're using a compiler that's smaller than C++11, then you should still go back and use the ampersand, bar, and the exclamation point. In many places in your program, you'll encounter statements of the following sort. If expression, statement 1, else statement 2. So basically, we are saying if the expression, evaluate the expression. If the expression evaluates to true, then execute statement 1, otherwise execute statement 2. There is a shortcut for these kinds of if-else statements. It's called the ternary conditional operator, which has the following syntax. So you're basically saying condition, which is the expression in here. So evaluate the condition. If the condition is true, so it's a question mark, in a sense, is the condition true? If the condition is true, execute expression 1, which corresponds to statement 1 in here. And if the condition is false, then execute expression 2, which is a column. So the syntax is condition, question mark, expression 1, column, expression 2. So let's look at some examples. These will be in example 14.cpp. Let's say we would like to compute the minimum value of two values, a and b. So the way we can do is, either we can write an if statement like this, or a better way is to write the ternary operator by saying evaluate a is less than b. If a is less than b, then the result is a, the minimum is a, otherwise the minimum is b. And basically taking the result of this expression, we assign it to the minimum variable, right? So it's basically the same as writing if a is less than b, then minimum is equal to a, else minimum is equal to b. Let's say you want to take the absolute value of a variable b. So we say, is b greater than or equal to 0, then the absolute value of b is b, because b is already positive. But if b is negative, then the absolute value of b is minus b. Let's go to the actual example. So let me put a breakpoint again in here and go through these statements. The ternary operator, ternary conditional operator. So again, x is minus 3, y is 4. So we are saying, is x less than y? Yes, x is 3, y is 4. So x is less than y. So we should be executing the x part, the if part, which is x. So this should return me the minimum value would be minus 3, right? And then we'll print that on the screen. We're now taking the absolute value of x. So basically we're saying if x is greater than or equal to 0, then the absolute value of x is x. Otherwise, the absolute value of x is minus x. And now you can see ABC becoming 3 because x was negative, and we took the absolute value of x, which is positive 3, and we print that on the screen. Here I'm testing whether y is odd or even, and we can do that by taking the modulo of y, modulo 2 of y. If the modulo 2 of y is 0, then the number has to be even, otherwise it has to be odd, right? So let's look at the value of y. The value of y is 4, so it's an even number. So look at the statement here. So evaluate y modulo 2 is equal to 0. If that's the case, you return me, in a sense, even. Otherwise, the result of this expression is odd. And this should be even, of course, because 4 is even. So basically, when you have these kinds of if-else statements, where you're evaluating an expression, something like this, the absolute value, the even, odd, the minimum, the maximum, then you would write these expressions using the ternary operator rather than an if-else statement. So let me do another example, a last example. So let's say I want to compute the maximum of x and y. I can write it like this. If x is greater than or equal to y, then the maximum value is x, else the maximum value is y, right? So this is one way to write it, but this looks ugly because you have an if-else statement. So instead of writing it like this, you can easily write it maximum is equal to, take this condition from here, so x greater than y. This is our condition. If this is true, then the result is x. Otherwise, the result is y. So this is using the ternary operator. This is using an if-else. And as you can see, this looks much cleaner compared to an if-else statement. So I can now erase everything and make this a single liner like this, and then print the maximum is, just print the maximum. And let me execute this so that you can see maximum of -3 and 4 is 4. As you can see, the maximum is 4. So bottom line, keep in mind that when you have only an if-else statement where you're computing something, try to convert it into a ternary operator like this, which looks a lot cleaner compared to the if-else statement.